Hey all, this is Robert Roach, host of the Type 1 Planet podcast. And today I had a conversation with Dr. Philipp Koellinger. He's the president of the board for the DeSci Foundation, which is an organization that's dedicated to the development of a more verifiable, more open, and fairer information ecosystem for science and scientists. So what does this have to do with becoming a Type 1 planet? Well, science and scientific research is one of the most important drivers for civilizational progress. Like every discovery in biology, physics, chemistry, they're all pieces of knowledge in the latticework that is our understanding of the reality that we live in. And the more we understand, the more we're able to manipulate and refine our own existence into one that has less suffering and greater potential for a sustainable future. What few people know is that the industry for scientific research and publication is really broken. It's driven by perverse incentive structures that push scientists to fabricate data, to select projects on the basis of cultural popularity than on scientific relevance. Scientists are scrambling to release as many papers as possible to secure their funding, which is creating a bubble in the scientific industry, and it's ready to pop. Scientists are disconnected and incentivized to hide information from each other, and it's in an industry where collaboration should be paramount. Now, my guest today, he's trying to fix the scientific information ecosystem, and he's using innovative blockchain technology to link every piece of scientific data, every discovery, every scientific document. It's on a living network. For example, if a scientific paper references a piece of data from another lab, that references a traceable link to the other document. And changes in the data will mean that all documents that reference the data will also change. So this system is designed to break down data silos in the scientific industry using a method that Dr. Koellinger calls Metascience, in which the scientific method is applied to find ways to improve the scientific industry. Well, I think it's a fantastic conversation. I'm only just scratching the surface here, but what DeSci is doing really has the potential to change all of science as we know it. So please enjoy, please listen, share, visit us at type1planet.net, check out our social media and follow us. We're starting to make a lot of connections now and starting to reach a lot of interesting people. And if you are aware of someone that should be on this show and you're aware of our mission, what we're trying to do, please reach out to us. Let us know. We look forward to hearing from you. All right. Hello and welcome to the Type 1 Planet podcast. I'm Robert Roach, and I'm joined by our guest, Dr. Philipp Koellinger. He's president of the board for the DeSci Foundation. And he's also the host of the Future of Science podcast, which we'll go into in a little bit. And the DeSci Foundation is an organization that's dedicated to the development of a more verifiable, more open and fair ecosystem for science and scientists. So Dr. Koellinger, thank you for joining me.
Thanks for having me, Robert. Pleasure to be here.
It's a pleasure to have you. So the mission of Type 1 Planet, we're hoping to reimagine civilization so we can enter into a long-term, sustainable state that's in equilibrium with ourselves and our planetary environment. And a major component of this model is to find ways to democratize scientific knowledge and to preserve its integrity and its verifiability while maintaining a viable industry for scientists to work in. So for the layman, let's begin with the problem that's being addressed by DeSci. What is the current state of the information ecosystem that's being used by scientists?
Right. So there's a lot of different parts to that. So I think we probably need to take a few minutes to actually describe the full scope of the problem. So let's start with the first one, which is how scientific information is currently stored and shared with the public. So the system that we're currently using is basically a system that derived out of the publication industry, the printing industry. So it's basically a model that is essentially 200 years old and which has only in the last 20 years or so made a gradual transition into the digital age. So what we have is basically a vast array of journals, of academic journals, that are doing peer review on the research that scientists are doing. And then that, the referees and the editors, they make a decision about whether a particular article is suitable and good enough for a journal. And if it is, then it is being published by that journal. And what happens then is basically one of two different things. So either it basically ends up behind a paywall. So that would mean that the article is being digitally released, but only to those few individuals or organizations in the world that actually have a subscription to that journal. That particular business model basically excludes the vast majority of mankind from access to the actual published articles. The other model is that the article gets published under an open access license, which means that in principle, anybody on the internet can actually see it and read it. But the authors then have to pay an author publication charge, which, depending on the journal, is anything between $1,000 or almost $12,000 per paper. Now, you can obviously see that there is big problems with both of these business models. So either we're basically excluding the vast majority of mankind from actually accessing that knowledge, or we have scientists who actually have to pay these enormous publication charges. And both of these business models actually create sort of like perverse incentives. So the one with the author publication charges, it actually creates an incentive for the journals to publish as much as they possibly can, right? And that gave rise to a bunch of predatory journals and journals that masquerade as scientific journals, but are actually not doing any sort of quality control whatsoever. And they're literally trying to just prey on scientists. So just because something got published in a journal doesn't mean that it's actually true. Just because it got published maybe even in a very prestigious journal, and this is where it actually gets quite worrying, it also doesn't mean that it's true. So let me dive into that a little bit more. So the way that very prestigious journals typically select articles for publication is based on a variety of criteria, but probably the most important one is how novel and how surprising the results are that the authors are presenting. And that means if you made a really breakthrough discovery, then you have a good chance to get into one of these glam journals, and they ultimately carry huge weight for the scientists to basically advance their career, to get promoted, to get a new job, whatever. So for the scientists, there's a huge incentive to actually try to make it into these so-called high-impact journals. Now, if the incentive really is that you should constantly try to do and to find things that are very novel and surprising, then, it does create perverse incentives for the scientists to actually cut corners or to massage their data or to literally just make up results just because they want to get into these high impact journals. So there have been a lot of cases in the last couple of years and even decades where we had cases of scientific frauds, where we had cases of publications that were very, very influential, that received thousands of citations, and that have literally triggered huge research programs that were sponsored, that collected like tens, if not hundreds of millions of different dollars. And that ultimately turn out to be false or based on fabricated results or based on results that did not replicate. And that is another sort of broken incentive that we currently have in the scientific system, which is that if you do find something that is really novel and surprising, you would actually want other scientists to independently check your results. So let's say you've run an experiment that yielded really surprising results, then ideally you would want to have an incentive mechanism for other scientists to basically take your experimental methods, to run the experiment independently in their own laboratory, and to try to see if they can actually replicate the results. Now, that would be a very sensible thing to do, because even if you can just replicate an original finding in its original form just once, you've actually dramatically increased the chance that that finding was not just an outlier and not just a perchance finding, right? But unfortunately, that incentive does not exist because, as I said, the journals primarily select for novelty and for surprise, which basically means that if you want to go out and just replicate exactly what somebody else has been doing, there is a very small chance that you will end up being able to publish that in a high impact journal. So that basically means that a very important part of the scientific mechanism to self-correct is currently missing, right? So that's one part of the problem. So the incentives and the publication system. There is a lot of other problems that we have. One of them has to do with the fact that a lot of data obviously is being created in science, and ultimately what you care about in a lot of data intensive or compute intensive fields of research is not even that much the article per se, but you actually care about the underlying scientific artifacts. So you care about the data and the code and everything that has to do with it, right? Now, the thing is that the traditional publishers, they do not have a business model either for storing these types of scientific artifacts or for actually evaluating them. So there is no mechanism for peer review or for even just making these scientific artifacts available to the broader scientific community. So that also creates a lot of problems. It means that a lot of the actual research cannot be independently verified. It cannot be checked. If you cannot go into the original resources, you cannot actually evaluate the original data, you cannot actually check the code, then you're very limited actually in how far you can really evaluate the quality of the research that has been done. But on top of that, there's also just a gigantic waste of resources because it is just so difficult now for other scientists to actually get access to these data, right? So there is a lot of money, a lot of time that gets wasted simply because these really important parts of the scientific enterprise do not get stored and do not get shared in a way that enables others to find them, to access them, and to reuse them.
Now, there's also the open access version that you mentioned, in which the authors, anyone can access the information, but the authors are being charged. Are there also perverse or kind of difficult incentive structures that are coming out of that system as well?
Yeah. So the author publication charges or these open access models, they have a number of really perverse incentives that come out of it. One of them is that they really create for the publisher basically an incentive to accept as many papers as they can, right? So because every time they say no to a paper, they actually say no to revenue. They say no to a contribution to their bottom line. Which is obviously a highly problematic incentive, especially if we keep thinking of journals as the mechanism that is doing quality control and curation for the scientific record, right? But it also creates a really weird side effect because it means that ultimately only institutions or scientists that are working at institutions that are very well funded can actually afford to pay these really, really expensive publication charges. And the authors that ultimately get funded, get published, they're the ones that are ultimately paying for all the work that the journal is doing, right? So they're actually indirectly sponsoring with their author publication charges all the other submissions and all the work that went into evaluating them that did not get published. So all of that is just, it's a really tricky system. And it's quite interesting to think about the implications of the White House memo. So there was the White House memo in September, where they basically mandated that all federally funded research needs to be publicly available, basically under an open access license. I think from 2025 or 2026 onwards, immediately from the moment where it's get published. So that ultimately means that scientists who receive funding from the federal government in the US, they cannot simply publish their results in the traditional subscription-based journals anymore. So that raises the question, so where else are they going to publish? Well, either they could publish under this open publication charge, author publication charge, which ultimately means that they would need to create sort of like a budget in their grant proposal that reserves money to pay for these outrageous author publication charges. And that means that they actually have less money available to do the real research, and they may actually go to journals that have perverse incentives of actually publishing stuff that is not really solid. So that is probably not an optimal solution, but it is currently the state of the system.
And I could see scientists saying, well, then I don't want to do federally funded research because I'd prefer to try to publish in Nature magazine where my research will get a ton of references and that kind of stuff.
Right.
So, all
Yeah.
right. So we're seeing over publishing, fudging results. We're selecting just for novelty and surprise, quality control issues, expense issues, all from this current system.
Yeah.
So let's bring it into the work that you're doing, the work that DeSci is doing. First, a clarification. What is the difference between DeSci Labs and the DeSci Foundation? Do they have separate strategic missions? How does
absolutely.
this work?
Yeah. So DeSci Labs is basically as a software company. So DeSci Labs is building infrastructure and technology for scientific publishing, and in the future also for novel mechanisms to actually finance and fund the research. And the DeSci Foundation is a nonprofit that is purely working on improving the scientific ecosystem at large. And we're doing that by setting up basically sponsoring programs that will help scientists to do best practice research, to investigate the current state of the scientific ecosystem by investing into Metascience research projects, and by also trying out new approaches of bringing together technology and scientists in ways that we can experiment and try to come up with alternatives to how the system actually could work. And ideally, we're going to do that in ways that are actual natural experiments, so that whenever we start experimenting with the system, that we actually don't do that in a way that cannot be evaluated, but rather we want to do it in a way that it is an experiment that can be evaluated and where we can actually see causes and effects. And then basically draw our conclusions and just feed that back into this engine that is supposed to increase the quality and the functionality of the scientific ecosystem at large.
Okay. So DeSci Labs is one of the major initiatives underneath the foundation, would you say?
They're two independent entities, but they have different missions. So DeSci Labs is a technology company. The DeSci Foundation is much broader in its focus. But of course, there's a collaboration between the two. So the foundation can, for example, in the future play a role in governing the ecosystem that DeSci Labs is building. It can also contribute to insights about whether the new things that we're building, whether they're actually working the way that they should be working. So we can have an independent layer of evaluation that keeps an eye on that system.
Okay. So let's dive into a little bit on DeSci Labs just to get an overview. So they say that they promote a radically open architecture for verifiable research. So what does this architecture actually look like? How does it function? How do users interface with it?
Yeah. So the bottom layer of what DeSci Labs is building is essentially something like a platinum open access publication platform, or maybe another way of phrasing it is basically a preprint server on steroids. So the infrastructure that is being built there. So currently it's in alpha testing. We'll go into beta testing later this month. So the first building block of that infrastructure is called DeSci nodes, and they enable researchers to basically create research objects. So fully interoperable digital research objects. So what's a research object? A research object could be any sort of scientific artifact. It could be a manuscript, it could be a data set, it could be a piece of code. It could be a video that is being recorded in the lab describing the experimental procedures. It could be a presentation that people have given. And all of these different components of a particular research project, they would be stored under the umbrella of a research object. That research object will then be stored on the decentralized web, meaning that it will be open to anybody to read and to access that information by definition. It's also built in a way that the data is being stored in a lot of different places around the world with a system that is called content addressing. So it's a real upgrade basically to the internet protocol that we're currently using, where the files and all the content on the current internet are basically the permanent identifiers. They're actually not permanent, but they're just links to a particular location of a server. So they tell you where a file is. They don't tell you what that file is. And under content addressing, that is being switched around. So in content addressing, basically each digital object has a unique identifier that is being derived literally from its content through a cryptographic hash function. So you can then verify that the address of that object actually matches the content that you're receiving. And then that content, as I said, is being stored by various data storage providers at various places around the world. So at minimum, it would be 5 different copies that are stored in, I think it's 5 different countries, 3 different continents. So it's vastly distributed, and it basically is the backbone of what we think that scientific record of the future should look like. Mm-hmm. It should not be possible to actually create paywalls around it. It should be possible for all scientists to actually create and to share their research results and the work that they're doing with the public for free. And then there can be a bunch of interesting tools built on top of that infrastructure, such as tools to curate knowledge, to basically summarize it or to surface it, very similar to what journals are nowadays doing. There's going to be tools to actually evaluate that research. So there's going to be a layer that will actually allow peer review and verification services provided by scientific societies. And there's a bunch of ideas that we have for how we can actually incentivize these scientists who are doing the work to actually do that work rigorously and to do it quickly. And of course, then there need to be revenue generating mechanisms that actually allow us to create these mechanisms. And so there's all that stuff that will come in the future. And then finally, because that entire infrastructure is built on the decentralized web, there is also a possibility to basically build a very efficient and very targeted funding infrastructure on top of all of that.
So let's go to the nodes real quick. I want to break it down from a total layman perspective. That let's say I am pursuing my PhD. I'm creating data sets around a thesis that I have.
Yep.
Each one of these data, let's say I create a data set, I can add it as a node. Let's say I have 20 of these nodes. I'll say, great, go to my PhD thesis defense. I get my PhD grade. I get it published. And now I have all of my data sets available here on this kind of node network, and including my final product and all of my my papers and maybe my presentations and that kind of stuff. And so those nodes are available if someone else were to continue my work in some other direction or wanted to reference one of my data sets, they would actually reference that particular node.
Yep. Exactly.
And they would say, okay, in my document, I'm referring to this node address here. And then would that apply as an actual reference on my research?
Exactly.
Okay.
That's exactly how it would work. So, and there is a number of additional superpowers of this new ecosystem that I haven't talked about yet. So one of them is that because we're building on content addressing and on actual persistent identifiers, there's also a very elegant way how this new infrastructure can then support versioning control. So that is also something that the current scientific record doesn't have, right? So if you basically want to update your manuscript, this is not possible the moment that this paper has actually been published. So there is basically only two things that you can do at that point. So either you write a new paper, which reports what needed to be changed, or you hand in basically an error message to the publisher, and they will publish a corrigendum saying that the original article was false, or you can basically withdraw your article, right? Same thing when you have data sets, right? So if you have data sets and you want to update them over time, what happens currently is that you just overwrite the original version. The old version either gets lost or it's very difficult to actually make reference to it. So in this new system, none of that is going to be a problem anymore. You can actually make very accurate references to specific versions of a research object or a data set. And you can also actually connect these research objects with each other. So you can now actually use citations as function calls. So you can literally start pulling in data just by referencing this particular part of a research object to pull it into your own one, or to run a compute job on a data set that is actually living in a different research object. So there will also be this possibility to actually do compute jobs on the servers where the data is already stored, instead of actually having to move the data around. So all of that is going to be possible.
It's so interesting. And so if a data set were to be updated or changed, let's say a data set further down this chain of citations, for example, if that data set were to be updated or changed, it would change all of the subsequential documents or citations or later data sets. Is that kind of how it would work?
Yeah. So how exactly the citations are going to be counted? This is something that will ultimately be in the hands of the people that are running the databases that are basically aggregating these citation counts. So we have some ideas about how this should actually work in practice. So the way that I'm thinking about it is that if you have these various components of a research object, then whenever somebody makes a reference to any particular part of that research object, be it the code, be it the data, if they pull it into their own research object or literally reference it in a manuscript, all of that should basically aggregate sort of to the root node of that research object, right? But ideally, if the databases that are calculating all these citation counts, if they would be capable of doing that, you could actually break that down, and you can say, well, within these research objects, how much of it has actually gone to the data? How much of the citations have gone to my code? How much have gone to my manuscript? And then there's also this really interesting idea that once a research object is out there, in principle, somebody else could come in and they could fork that research object, right? Very similar to how you're currently writing code in GitHub. So you could come in as a scientist and you could say, oh, this is actually quite interesting. I'm gonna take that data set, I'm gonna take that code, but I'm going to add something to it, and I'm gonna write a new paper out of it. And then you could either create a new version, sort of like a forked version, or you could say, well, actually, I've done that work, but I would actually like to merge my work with the work of the original authors. So you could send them a merge request, and it would be up to the original authors to decide whether they actually accept that merge request or not. Cool. And that would create really interesting new models how scientists can actually work together, right? So you could then imagine that there could be basically an ecosystem of people that are adding value to the work that others have been doing in a lot of different ways. For example, by doing additional robustness checks or analysis, or by literally repeating their experiment in a different setting, or maybe just also adding to how the original research object is being presented. For example, by writing a nice summary that is accessible to a broader public, or by creating a piece of art that is illustrating the results of that research object. Right? All of these things, in principle, they will be possible.
So, and now you're starting to delve into the culture of the scientific community and the
Right.
collaborative nature. And because right now, it's very interesting from an outsider's perspective to see scientists talk about how competitive it is, how secretive it can be. You're hiding, you're siloing your information. You don't
Yeah.
want to present it too early. You want to be
Yeah.
the first, the first person on a certain idea. And
Exactly.
it's just
All of
not
that.
the way that
Yep.
you would think science should be operating. It should be as collaborative as humanly possible.
Yeah. Yeah,
So,
exactly. And you're 100% right about that. It's all of that, all of these sort of like weird incentives that we currently have in science, where people are siloing their data, and where they're being secretive and non cooperative. All of that are sort of like side effects of the broken incentives and the imperfect infrastructure that we currently have. And we actually think that a lot of that can be fixed with a better infrastructure that actually allows people to get credit for doing the right thing, for doing best practice, for putting everything out in the open, and also to get credit for being collaborative and building on the work of others, and potentially joining forces in a way that everybody will ultimately get credit for it.
hmm. So let's expand out now from the DeSci Labs to the DeSci Foundation. And you actually mentioned a term that I want to dive into a little bit, which is meta science.
Metascience, yes.
And so, what is meta science? What are these research centers that are looking at how science is actually being performed?
Yeah. So meta science is basically a part of science that has emerged in the last few decades, sort of like as a grassroots movement, where scientists across various disciplines have begun to basically turn the eyes of the scientific method on the scientific corpus itself. So they've begun to study how healthy the scientific record is. So a very large part of meta science, as it's currently being carried out, is actually attempts to figure out how replicable and how robust the important results in the scientific literature really are. And what we've learned from the first few waves of these meta scientific, mostly replication studies, is that there is a substantial replication crisis that extends across a lot of different fields. Some fields are more affected by it than others, but it turns out that on average, about 50% or so of the results that actually get published can ultimately be independently replicated by other researchers. So it's a coin flip. And in some fields of science, for example, in a field of science, so biomedical research, for example, preclinical studies that ultimately lead to, or should lead to, the discovery of new drugs or new cures for diseases, this replication problem is much, much worse. So there have been studies basically showing that in preclinical trials or preclinical studies for cancer drugs, less than 10% of the published results in top journals actually replicate, and that's a disaster, right? So that's really one of the first things that we learned from meta science. But meta science is not only replication studies; it's just generally this idea that we can apply the scientific methods to science itself to figure out what is working and what is not working, and potentially also to develop solutions for that. So you can also think in the future that a part of meta science could be things like theoretical studies, where you do mechanism design, where you actually sit down and you say, okay, so we have identified a problem in how the incentives in a particular field of science are, or in a particular part of the scientific process. And we now sit down and we try to come up with a better incentive system, a better mechanism. And you can do that, for example, with the tools of game theory or with computer simulations. And then you could take these theoretical predictions about how this better system should perform. You could take that to the field and you could test it. And you could compare it to how the current system performs, right? So this is actually how I'm thinking about how Metascience could evolve in the future. So not only looking at the replicability of studies that have already been published, but much more broadly thinking in a very structured and scientifically rigorous ways about ways how we can actually improve the way we do science.
So, I mean, just from the get-go, for listeners, the scientific method asks for your results to be 100% replicable, so, and that it's and by doing that, it's a fact. If you mentioned what is true and what is not true earlier.
Oh, it would be so nice if that would be that simple. I mean, yes, right. This is. I mean, theoretically, right. This is how people are typically thinking about it. But in reality, of course, this is not how it works. So, especially when you look at empirical research, so if you do like any sort of statistical testing, there is a probability that the results that you're looking at are that they were just the result of chance, right? And yes, you can actually reduce that probability through various ways, such as increasing your sample size or using more powerful statistical methods or whatever it be. But it is almost impossible to actually say that something is 100% replicable. So this is a target that we cannot even achieve theoretically. So there will always be a margin of error where, we just have to accept that even, very, very convincing results that have been published in top journals may actually not independently replicate. The only way for us to actually figure that out is to try it.
So the metascientific method is our theories are what are these different potential systems of science that from which we can create new data, and that are minimizing the margin of error in terms of the this replication crisis that you're talking about, and then take those ideas into the field. Let's experiment. Is this kind of experimentation happening yet in labs, or are you approaching institutions and saying, hey, we want to try this out? Like, how does this work?
So we definitely did not get to the point yet where we can actually do this sort of mechanism design in a scientifically robust way. So the DeSci Foundation was only started like 1.5 years ago, and basically we're still in the process of actually trying to get donations from people so that we can actually have a funding program that will help us to actually finance these research centers. The research centers, they will be very expensive to run. I think what we can actually do in the short run is we can help scientists with funding programs, for example, to make their data publicly available, to basically cover their storage fees. We can also have prizes that reward scientists for best practice. And these are sort of like things that we can do at the beginning that are going to be scalable and not horribly expensive. But for us to actually branch into this larger idea of running these research centers and actually doing a lot of these different meta scientific studies on different parts of the scientific endeavor, I think that will take some time, and there's a question mark about whether we will actually have enough money in our hands to do that.
Interesting. Okay. Well, and the other side of it from an implementation perspective is I wonder if how does the DeSci Labs methodology plan to incorporate the institutional publication platforms like JSTOR and Science Direct, because we have a body of information that already exists, but it's behind these paywalls. So is it possible to incorporate that that institutional previously collected knowledge?
Yeah, I mean, to some extent, this is possible, and the extent to which it is possible depends on the license agreements under which the original content was published. So if something has been published under a Creative Commons license or an open access license, that in principle allows others to take those results or those publications and to post them in a different format, then yes, that's possible. There's also possibilities to actually find so-called preprint versions of articles that ultimately ended up behind paywalls, so that we cannot actually directly put into this new system. But there may be versions of those papers that are identical or relatively close to the final version that we can actually integrate. And in principle, we can also just create a platform where scientists can then finally store and share the scientific artifacts that actually are part of these publications, but are currently not shared with the public, for which there was currently until now, there was no really good infrastructure of doing that. So we can actually do all of these things. Some of it will require the input from scientists. Some of it can actually be automated. And then there is the question, of course, of how do we integrate this new version of the scientific record that we're trying to build with the data about the scientific record that we already have. And that data is very important for actually finding the original work, for counting references, for seeing who has funded what, who has what type of importance. So we're in ongoing talks with people in the scientific publication industry to figure out how we can actually do that. There's ways how the existing metadata about the scientific record can be integrated with the metadata that will come out of this open system that we're building.
The word that kind of comes to my mind about the current existing system is that it seems like a bit of a bubble, where we have a swelling amount of these papers and findings that are products of perverse incentives, and that there seems to be a legitimacy bubble here that is getting pretty big and might pop. And is that, do we need to change the scientific information ecosystem in such a way to prevent its own collapse or to prevent some sort of existential crisis for that ecosystem?
I'm just going to give you my personal opinion on that. And my personal opinion is, yes, we do need really radical change. You're totally right. So what we've seen in the last couple of years or decades is actually an almost exponential increase in the number of scientific publications. So there's a lot of different reasons for that. One of them is that the incentives for scientists have more and more shifted towards quantitative markers of productivity. So if the only way for a scientist to make progress in their career is to publish or perish, or to have a lot of impact or perish, then it is not surprising that you actually create this flood of new publications, right? So what happens is that they start slicing one big result or one big data set into smaller and smaller pieces. That there is a lot of incentives to publish things that are ultimately not worth publishing. And yes, so you have this increase, it's almost exponential increase in the number of publications. But at the same time, there's also increasing empirical evidence that the actual impact that the science that we're currently doing is having on the real world is getting smaller and smaller. So in economic terms, it means that we see increasing evidence that there is decreasing returns to the investments into scientific research and into research and development, broadly speaking. And that really is a fundamental problem for mankind, because the rate at which we can actually innovate and do technological progress and have scientific progress is ultimately responsible for our ability to have economic growth. And it is also responsible or directly linked to our ability to respond to new crises and to find solutions to problems that may actually threaten mankind. So if there is a substantial decrease to the returns to investments in scientific research, there's basically there's only very few things that we can do about that. One is we can invest more and more money into this machine that is getting less and less effective. Or we can try to find ways how we can actually increase the productivity. So basically change the production function. This is really what we're trying to do. So we're thinking that by reorganizing the way that that science is being done and being evaluated and being shared with the public, that we can actually increase the productivity of these investments into research and development and science. But there's also a much more pessimistic interpretation of these empirical results that suggest that the returns to R&D are actually decreasing over time. And that is the interpretation that maybe it is just getting harder and harder to find good ideas, because the good ideas that are easy to find, they have already been found, right? So we've already harvested the low-hanging fruit, and to get to the higher-hanging fruit, we just have to put more and more effort into it. And that is actually a very, very plausible explanation. And if that should be true, we're really in for a rough ride, because it means that even if we improve the scientific system, there is no way for us to actually maintain the level of technological progress or economic growth that we currently have, at least not indefinitely. And if we want to do it, it will require larger and larger investments into research and development, which basically means we need more and more funding, larger parts of GDP that need to be going back into research, into science, a larger part of the population that actually needs to work in science. And that is ultimately, there is natural maxima to how far we can go with that. Right. So if that is the reality that we're facing, then ultimately it means that economic growth and technological progress will at some point come to a standstill.
Wow. And so let's change the paradigm there for a second in terms of this vision for the future. What's the grand vision of this kind of technology? What's the best case scenario for a scientific information ecosystem? And how would that change the way that our civilization works?
Yeah. So I think the best case scenario is that we build a system that is as productive and efficient as it possibly can. Meaning that for each dollar that we put into that system, we're getting out the maximum amount of actually true and useful knowledge that is possible. So doing that is going to be a major, major lift. And as we said earlier, it will require a major deviation from how we're currently doing science. So we may be able to actually, increase these returns to investments into R&D and into science by doing that.
Wow. So I feel like we're just like scratching the surface here in terms of what you're doing. And I genuinely hesitate to go on, because I want my co-host to be on here, Dr. Alexandra McCall-Garfinkel. She wants to jump into the funding models that you mentioned.
Right.
She wants to jump into kind of a deeper overview. So I think this is a good place for us to stop for now. I promise.
Sounds good.
I would love to have you back on. A final question. Who else should we be talking to? Who are other disruptors in this space that the DeSci Foundation, DeSci Labs respect, want to work with? And who would you want to sit down at a table with to just talk about these issues?
Yeah. So I think that there is a lot of people in the scientific community, especially in people that are doing meta science, that have actually thought about many of these things, that are worth talking to. And we're also always in the process of actually trying to scout and to find these people and to bring them into our Future of Science podcast. So, one thing that you can do is just look at the people that we've already invited. So they were all like, they were fulfilling that criteria that you just mentioned.
Okay, excellent.
So they were all people that we wanted to talk to because we thought that they have something interesting to say. But of course, there's a lot of other people out there that are not even on our radar yet. So I'm sure that there is a lot of people in science, but also in technology, maybe even in philosophy, and maybe even also in not so closely research related sectors, such as, let's say, investment or politics, where you may find people that have thought very deeply about these things and have something interesting to say about it.
Well, Philipp, thank you so much for jumping on with me today. This is incredibly fascinating. I have like 100 more questions, and we're just going to have to cut it off here for now. I really appreciate it. Where can our listeners find you, follow you, the DeSci Foundation labs, everything? Where would you send us?
Yeah, so the DeSci Foundation is just the DeSciFoundation.org, and we have our seminar series there. We have the recordings of all the seminars. We have the podcast there. You can find the podcast also on Spotify and on iTunes. DeSci Labs can be found at DeSci.com. And from there, you can find all different sorts of information about the system that they're building. And you can also start creating research notes yourself. And and me you can find on Twitter or
okay,
I guess
awesome.
Also via email. The old-fashioned
way. That's how I gotcha. I will link all of that in the show notes. Go check it out. Please check out the Future of Science podcast. I'm going to. Philipp, thank you so much. This was an amazing conversation.
Wonderful. Thanks for having me, Robert.
It's a pleasure.